So we saw in the last section how to graph functions, mostly using the computer when we have a function of the form f of x, y, where we have two variables x and y. In this section, we're going to see a way to represent that information in just two dimensions. So this is something like that you've likely seen often in your life, but maybe just not thought of it in this particular context. So let's start with an example here of a topographic map of Yosemite National Park. So if we look at these lines going through following one of these, the picture is too small here, but there are numbers on some of these. And so what a topographic map is telling you is rather than drawing this little Yosemite Valley here in 3 dimensions, we draw it on a 2-dimensional sheet because it's easier for us to work with, but then we draw curves on it that represent the heights in the valley. So what this means is if I follow along this curve here, I'm staying the same height the whole time. And so this gives us a way to represent this information, this 3-dimensional information in 2 dimensions. You've likely seen this also with things like weather maps where it shows temperature curves. So along this curve, the temperature stays the same and things like that. So let's go ahead and see how this is actually working with some functions. So this is one of the more important concepts in this course because it is a way that we can represent 3-dimensional data in 2 dimensions, and it does come up a lot, as I just explained. So we're going to refer to these not as topographic maps, but as contour plots for our function z equals f of x, y. You can do this with 3 dimensions as well, and then your contours are surfaces in 3 dimensions, but we're mostly going to stick to 2-dimensional ones. So what we do to get a contour plot is we fix some various fixed values of z, and we plot the curves c. So if we fix z to be some value c, we plot the curve c is equal to f of xy in the xy plane. And then what we'll do is we'll write whatever value c we have there next to the curve to indicate its value. So like I said, this gives us a way to view 3-dimensional data in 2 dimensions. So let's consider this function z is equal to 10 minus x squared minus 2y squared. So this is one of the graphs we gave in the last flipped class video. So just to refresh our memory, it looks something like this, so kind of an upside down bowl. And so what we can do is we can fix a value of this and look at the curve that gives us that. So in this case, I've fixed the value where z is equal to 5. And you can see if you walk along this blue curve here, you stay at the same height of z is equal to 5 the whole way. So what we'll do now is we'll take this curve and we project it down into the xy plane, which is somewhere down here. See where the z is equal to 0. That's going to be our xy plane. And we project this down to get a 2-dimensional representation of this curve. So see, we have this 2-dimensional representation here, and we label this with a z equals 5 next to it if we were drawing just the contour plot. And we do this for a bunch of different values of z, and it gives us an idea of what's happening with our surface. So here we can see if I plot a bunch of different values, it's going to look something like this because the fixed values of z are ellipses in this case. So look back at our equation here. If we take a fixed value of z, we can subtract it to the other side, bring the x squared minus 2y squared over, and we get an ellipse. So we can see as we follow this ellipse along, this is the value z is equal to minus 50, z is equal to minus 100, z is equal to minus 150, and so on. So we can see that if we walk in a fixed value of z, we walk in an ellipse, and as we move closer to 0, 0, our values of z are getting bigger. So we can kind of imagine that's what this is looking like. We're walking along these curves, and as we get higher values of z, we're getting smaller ellipses going up. And we can also represent this in with colors as well, which is the way Mathematica will give it to you if you just ask for a contour plot and not anything else. Don't put any specifications, but this is how you normally draw it if you were drawing it by hand. And we'll see how to do those in class by hand. So let's see a couple of other examples of this. So another function we looked at last video is sine x plus cosine x. So remember, this was this messy kind of up and down bumps everywhere. So notice some of these are going up to 2 and some of them are going down to -2 and somewhere in between with these waves. So if we fix a value of z, what is this going to look like? Well, it looks messy like this here, but we can see, well, these ones, you can see this is going up as we go closer to the center. So we have 0.72, 0.86, 1.8, 1.4. for it, and they're kind of going up. And then we have these lines here where the value of z is 0. And then we have the ones going down as well, these negative ones. So if we think of what this is looking like, we're getting these circles here as we're going up towards the top or as we go down towards the bottom. And then there's these values where z is just equal to 0 as you go along the curve as well. So that's what this one would be telling us, is a bunch of bumps that go up and down. And if we look at this graphically, with colors, with this one, normally the colors maybe aren't the most helpful things, but sometimes they are. So for this one, it really highlights that these ones are the ones going up to the top at z equals 2, and these ones are going down. So the positive and negative is really emphasized here with the different colors. And finally, let's look at this function z is equal to square root of x squared plus y squared. So this is going to give us a cone. We could see that by saying if y is equal to 0, then z is equal to square root of x squared. So it would give us plus and minus. So square root of x squared is absolute value of x. So we get the absolute value function, and same thing for y, and then just think of filling those in. So it looks something like this surface here in red. And we can think of, if we fix different values of z, well, the smallest value we can get is 0, and then they're going to be circles as we go up. Because if I fix a value of z, say z is equal to 2, well, if I square both sides, I get 4 is equal to x squared plus y squared, which is just a circle of radius 2. So here's our values for this, and you can see as we go towards the center here, the values are getting smaller and smaller, which makes sense because we're getting closer and closer to 0. And as we go, as we go away from it here, we're getting larger and larger values as it goes up. And we can also view this with color as well, like this. So you can see kind of the smallest value here is in blue, and then gets lighter as you go up. So we're going to use these contour plots to get lots of information. So for now, we can kind of see what the function is doing with different values and how the fixed values of z, what curves those give us. We'll also look at in the future sections how the function changes as you go in a particular direction by using the contour plot.